Timber bridges have been around Atlantic Canada for a long time as well. In fact, in the old days, at the turn of the century in New Brunswick, over 75% of the bridge inventory was timber. And in 1915, in the bridges being constructed, 80% were being constructed in timber. In our community in New Brunswick, for example, there's about 2,800 timber bridges, 54 covered bridges, down from 400. And in Atlantic Canada, somewhere in the 5,000 timber bridge range exist. This does not include railway bridges, does not include off-road bridges or PED bridges. So as you can see, quite a few bridges. And of course, we're known in New Brunswick for the longest covered bridge in the world, the Heartland Bridge, a multi-spanned covered bridge that they maintain and keep up for use with the public. And this bridge goes through all seasons, not just summer, winter, and spring and fall. And so these bridges have stood the test of time for a long time through many seasons. This is a shot of a class that I taught, a level 1 class in Moncton for timber bridges. And we took them out to Petty-Kodiak to that covered bridge there. And this is what gave me my incentive to get into timber bridges. This is Sawmill Creek covered bridge in Hopewell Hill, New Brunswick, down toward the park from Moncton. And you can see this 33-meter long covered bridge built in 1905. And the sign says, "Walk your horse or pay a fine." And that was a standard way to build bridges at the turn of the century. Well, they didn't put this cover on the bridge so that they had a place to go in and yell, "Echo," or to kiss their girlfriend, or to hide the horses from the rain or snow. The reason these bridges were covered had nothing to do with that. The European designers knew something, and that is that if they put a cover over their old howe trusses, their timber trusses, they would last a lot longer because it would keep the moisture away from the connectors, as you can see here, and allow the bridge to go a long time in service. You can see this traditional method of maintaining the bridge and increasing strength we'll talk about in subsequent webinars. But this is called a hog jaw. And basically what it does is it puts a cable from one end of the bridge to the other, and then they have nuts here on these cables and can tighten them and put bearing up underneath this tension cord. And they do this when they don't understand the timber bridge and understand its capabilities, and they're trying to strengthen it. Well, the steel expands in the summer because, of course, the coefficient of thermal expansion of steel is 3 or 4 or 5 times that of timber, depending on species. And what happens when you install this in the spring when it's cooler? In the summer, it heats up, expands, and gets loose. And in the winter, it contracts and gets tight. And so you really never know whether this is engaged, and what we really call them are catcher's mitts, because they're there in the event something fails. And you can see this replacement timber probably wasn't chosen because that's a tension element, and you can see the size of the knot. And slope of grain determines strength and tension elements. So these bridges were not just thrown together. The ideas were to protect, preserve, and extend life, even to the extent of the skirting here, which would keep blown in rain and wind from getting at that connector below. Just in Russagornish, you can see this full pictured along the bridge. Well, people say, well, that's so they can look out. Well, it had nothing to do with that at all. It had to do with letting wind in, because these covered bridges pick up a lot of side wind, and that's a big part of their design. And you know, the nemesis, these are the kind of the Achilles heel. This is the end of a truss in a covered bridge where a vertical fastener has been used to go down through the seat, and it's let blown in water get in there and inside the wood, and it's decayed. And you can see this outline here. That's the outline of the heel assembly of the hog jaw, which has prevented moisture from evaporating from the surface and accelerated decay. And that's what led to this. You can see in this picture here, I think a few years back, you can remember this video. This is Cherryville Bridge, and you know, up near Coles Island, and it became dislodged from the seat because of the decay of the seat. So what I want to draw your attention to here is the fact that this bridge, this bridge is going to mess me up. This bridge is the access for that community. And when it floats away down the river, they've lost access. And a second detail in there is that why did that bridge all of a sudden decide to sail down the river? I mean, it wasn't the only time the bridge had floodwaters go under it in 100 years. The water had always, during floods from time to time, come up and licked away at the side of the bridge. Debris fields would get there. Why was it? Well, it was because vertical fasteners had been used at the end behind the heel plate assemblies, and improper inspection techniques had prevented them from finding out if the bridge had problems, and it was too late once the bridge was sailing down the river. But the interesting point about it is that the bridge didn't just sail down the river, it sailed down intact. And not only that, they had to pay a contractor to get the bridge out from the concrete pier that it lodged up against. And the contractor turned around and sold the wood out of the bridge. Enough wood was there to build 7 chalets down on the St. John coast. So the wood that was there was still good. And what was going wrong? It was the areas where they hadn't properly inspected and kept up with maintenance. So a new covered bridge can be designed and built. See, Cherryville, this is a design I have out for the replacement of this particular bridge. So timber's use declined in the 20th century. We know that it was displaced by steel and concrete. Why was it displaced? I mean, why did over a period of time wood become used less and less and less? After the Second World War, the GI Bill, and the military soldiers all came home, we started to see the advent of the growth of our highway system. And by the 60s, steel and concrete were kind of coming into play. And by the 70s, when I went to school, wood was beginning to fall out of vogue. It was the beginning of the great panacea of precast concrete. People felt that precast concrete would span longer distances, carry more loads, and of course, provide longevity, which timber bridges, they, in their opinion, didn't have. But of course, we just know that's not true. And what happens here? What happened to the registry of bridges, and how many bridges did we have? Well, you can see here in front of you, the screen talks about the number of bridges. Right today, including railway bridges and off secondary road bridges, we would have just over 900,000 total bridges in North America, of which around 265,000 are timber. And when you consider companies like Union Pacific, they own 40,000 timber bridges themselves that are not in the highway registry. So there's still a lot of timber bridges out there. In fact, existing bridge inventory is about 7%, and annual construction in timber is about 1%. And we are seeing a great change in this right now because of carbon trading and other issues, which we'll talk about in this webinar. And as I said earlier, in Atlantic Canada, we have at least 5,000 timber bridges. In New Brunswick, 2,800, Nova Scotia, 1,800. And this probably represents, I estimate, about 50% of the total bridges in Atlantic Canada. Timber bridge superstructure types. What kinds of timber bridges do we see? Well, you can have a log beam underneath here. This is a round log girder system with simple abutment supports and a simple single lane. And around the world, in many countries, this is a very typical bridge still in service. And we might see these spans, typically this should be 30 feet, not 30 meters. 10, 12, 13 meters are about the longest in a log girder that you would see in a bridge. And you can see here this multiple span highway over a rail system bridge with multiple log girders placed close on corbels. We often refer to corbels as landings. And what were corbels used for? Well, These log girders might have not all been the same length, and these provided a landing. But remember, engineers in the group, the corbel does not shorten the effective span. Contrary to public opinion, even if you put a vertical bolt up here, which you shouldn't, and crack all these corbels, which you can see going on, they do not shorten the span. We would have dimension timber bents, as you can see here in this bridge over a railway track, an overpass bridge. As you can see here with dimension timber girders and this dimension timber bent system. You can see a bent system here. This is a replacement bridge with a cantilevered superstructure, a curved glulam super cantilevered with drop-ins over the rail to reduce the height of the superstructure over the rail corridor. It's another one here you can see with a slope cut at the end of the cantilever portion to let the trains go through with a shorter depth here. Another little trick in design that we use for designing overpass bridges. Another type of timber bridge you have is what we call pre-stressed. And you can see basically 2x14s here, side packed, holes drilled all the way through the piece, and a big plate and a big through bolt, a through rod, and they're tightened up to form a superstructure where the deck and the super are one and the same, and then they can asphalt over this if they so choose. And you can see these are bents here, and sometimes these bents have been modified and converted from what we call a pile bent, where the pile is driven into the ground and the headers on here and the super rest on that, and we switch those out and put in a frame bent on top of the pile stubs and create a frame bent scenario for the sub, and the superstructure in this particular case is pre-stressed laminations, vertically laminated without glue laminations of, in this case, Doug fir. Underneath you can see the piles that can be dimension timber or they can be round timber. You can see this guy's been healed up with a wrap and injection of a 2-part slow cure epoxy to build strength. And you can see this cap here working forward. This is another little interesting old bridge, 140 years old. You can see these hanger rods here going from the compression cord, and these are the webs. And you can see the webs here, one direction only on this side, one direction only here. Now, this is an interesting bridge because of one of the features that I like to refer to in this bridge, because Percy Allen is a very famous engineer in Australia, and he designed this bridge. And you can see this hanger rod assembly. They painted the bridge. You never paint with more than 29% solids on heavy dimension timber because it holds the moisture in. Even the best paints won't flex, and they become brittle and flake off and hold moisture and lead to decay. They accelerate decay. Always use less than 29% solids stains on your heavy dimension timber bridges. And this bridge, as you can see here, all with the hanger rods and these compression webs. This is a Dare truss bridge. It's a Percy Allen bridge with the X in the middle, very typical Percy Allen bridge. You can see the compression webs, and then you see the X in the middle, that's a Percy. And then you see this MC channel has been used to replace the tension cords, and that's called a Dare truss. And then transverse shear girders for outrigger placement to provide lateral stability in this pony truss. You can also see through trusses. This is down at in Fundy National Park in New Brunswick. And you can see it's a through truss here with a how truss typically and hanger rods. And then this is a nail laminated, vertically laminated longitudinal deck that rests on floor beams. And one of the issues with our bridges, covered bridges in New Brunswick, is that our floor beams traditionally rest between node points, which means they introduce bending loads to the tension cords at the same time they have axial tension stresses. And a better design for our how trusses is to head them off at the nodes. And in the conversion designs for covered bridges, I like to do that. So another one here, you can see out in British Columbia, where the engineer of record decided that they didn't want to see the bridge last much longer, and they put all this bent metal on it. And every day that the moisture, time, and temperature changes, that sweats. So if you're ever going to go to some idea like this, it's called bent metal. Make sure that it's suspended off of the wood by at least 1/4 of an inch to let it have a chance to breathe and not sweat on the wood all the time. This is a howe truss, deck truss, basically where the howe truss is under the deck. It's in Dawson Creek. I designed a restoration for this for CNR. It was their longest truss in their system that they have, where it was found to have a capacity of 25,000 pounds per axle. We increased its capacity to 80,000 pound axle by reinforcing it, as you can see here in picture. And this gives you an idea of what's going on. This is a video of 30 men lined up to retrofit the bottom of these plies that are in each of these, each side of this howe truss under. And in 55 minutes, they have to put a full length retro on the bottom of this. And it consists of full length reinforced polymer, which is 5 times the strength of steel at 1/5 the dead weight, and acts to provide a much better solution to fix a truss than, of course, I have to come out each time to do this, than than a hogjaw would, as you can see here, completed. This is after it's finished. We treated it with copper naphthenate, and I ran the Brent car across it to do a test, make sure everything was right. This is a Hammond River covered bridge in New Brunswick, where this beautiful long covered bridge had a design restoration, and they had a mishap because these floor beams are not typically spiked to the tension cords. They just rest there, and the deck spans them, and they walked on it with a crawler, and the track pulled the floor beam laterally, and a combination of decay and a lateral pull displaced the floor beam, and down it went. Not a pretty picture, and of course leads to a negative thought about covered bridges. And it ended up with this one. They stripped it back and got too far in without having the proper design understanding and inspection understanding, and ended up taking it out, and that sits there today, which was a shame to lose one of our covered bridges in favor of a steel Bailey bridge because of something like this. So we're on Milky right now. I've designed a solution for this Milky Bridge near St. John's, a 2-spanner, about 115 feet a span. You can see it here. This is showing you underneath the hanging scaffolding. And I was just there this morning, as I tell you. And I designed 2 35-meter long Glulam beams, one to go on each side. You can see the tracks. This is how we roll them on. And the nifty thing about these beams is that the end dead weight of each beam is less than the current design capacity of the bridge, which is rated at 5 tons. And we're going to raise this bridge rating to 30 tons to allow fire trucks to get through, and snow plows and so on, because now the province has to stop their snow plow at the mouth of the bridge and have it plowed privately. And that causes a lot of problems. So we wheeled these on with the tracks, as you can see here, just basically cable them on. And these great big long beams, 35-meter clear span, they extended out because we have other things to do with them, so they're just used temporarily. And they extend through the bridge. We block them up to support them off the pier and the abutments. And we have FEMs, you hear them, fixed end moment connections, that allow these beams in 2 parts, because you can only ship 17 meters, and they're 35 meters long. And we fire test, who knows? Sorry. You can see here this FEM basically is providing for the longer. False alarm. Okay, we'll see if I can keep on going. And this is what we're doing to the bottom of the truss, as you can see here. We're basically shear paneling the side of the truss to compensate for shear failures created by these floor beams where they've been overloaded. And then this tension cord here has a piece of high strength fiber underneath it, and a Glulam Packer beam, as you can see here, to increase the stiffness. And this allows us to restore this truss to bring it up to a 30-ton rating. Well, these.
Hey Dan, is
yeah.
that coming from the hotel?
Yeah, it's a hotel.
Okay. Yeah, it probably won't go on for too long there. So
I'm
yeah,
hoping it's just I hope that they're just doing a test.
yeah, I'm sure that's probably what it is there, but we can still hear you anyway. So
I don't know what else to say. Nothing to be done about it, I guess. This shows here what we call embedded corrosion. And I wanted to talk about this for a bit because everybody talks about steel and concrete lasting longer than timber. Well, as you can see here in this particular case, they're what we call embedded and exposed corrosion zones in North America. And in New Brunswick and out in the Maritimes, we have the highest exposed corrosion zones. And of course, the reason for that is that the trade winds tend to blow up from the southeast a good part of the year, and it harbors the salt-laden air in and around the fjords and inlets and holds them next to these timber bridges. And the metal that's in a timber bridge, as you can see here, would get impacted and by these zones. As you can see here, this is the impact in Milky's on the hanger rods of the embedded corrosion. This is the outside of that's like hitting your head with a hammer, isn't it, guys? It feels so good when it stops. You can see this is the hanger rod, the King hanger rod, and its diameter exposed was about 2.5 inches. It was designed at 2 5/8. It had lost this kind of diameter outside the wood areas where it was exposed, and inside the wood areas, here's what it had come down to. So all the hanger rods had been affected by embedded corrosion in the bridge, and thus we had to replace those as well. This was unseen, and you couldn't tell even with continuity testing what was going on inside the wood. It's called embedded corrosion. This is the stitching bolts that connect the two pieces of, because there are multiple tension pieces of wood in the tension cord of a Howe truss. And this is Milky's, a piece out of Milky's. This is a stitching bolt. You can see what thickness it was at the ends. And inside, where it passed through the double cords and the packers, here's what it had depleted to by rusting. And so this showed you exposed and embedded corrosion problems that go on in these bridges and are so important to be keeping a mind on when you're inspecting bridges. So steel, of course, has its problems as well. This is down in Amherst. It's the one we featured on the cover page, Francis Bacon Bridge, and or better known as the Rainbow Bridge. And it was originally a timber bridge. And then 47 years ago, they decided to get a longer span. So they took a pile band out of the river, cut it down, and put a bunch of other piles on the end and put this steel pony bent bridge in place. And after not keeping up with primer and painting in the highest embedded and exposed corrosion zone in the country, here comes the result. And this is 48 years of service. Now, remember, I said that we stopped building timber bridges in the 50s and 60s because they didn't last. The timber bridge that this bridge replaced, this bridge here replaced, had been there in service already 70 years. This bridge only lasted 48 years, and we put this new bridge on those old piles. Some of them were 80 years old at that time, and we basically built a new timber bridge on the old piles, and this timber bridge has a 100-year design life, and the steel one was done at 48 years. So when I hear the notes that timber doesn't last and steel and concrete does, I think to myself, well, it's because they don't know. Because all these timber bridges that I'm showing you have lasted longer than the steel one did in Amherst. This is a suspension bridge up in the Yukon. again, lasted. We restored this bridge, going the distance, lasting a long time. So timber bridge service lives, are often impacted by the perception that they don't last, and it's an improper perception. Yes, timber is susceptible to decay. As with any material, timber will decay if it's not properly designed and maintained. For timber, the most common form of deterioration is decay. 82% of all timber bridge degradation is caused by decay, fungal decay, 82%. And decay can easily be prevented through careful design, chemical preservatives, and proper ongoing maintenance. Look, if you think concrete lasts, look at these concrete bridge pictures. Look at these concrete bridge pictures. I'm on this handbook committee for AREMA, and I get all of these pictures from students that come to my courses. This is the greatest infrastructure disaster in Canada, the greatest. It's Gardiner Express Parkway outside of Toronto. And in Toronto, they're spending $1.8 billion to fix concrete bridges with an average age of 32 years. Yet timber doesn't last. You see, and when you don't fix it and when you don't look after it, this is what happens. And no one wants this. We don't want bridges to fall on people, but yet we have to maintain them. And so somehow we've got into this misplaced idea that concrete and steel last and timber doesn't. Now, steel has its own problems. This is rust-resistant steel, which the province of Nova Scotia won't use and doesn't allow in their specs. Why? Because in salt-laden air around coastlines, the patina of moisture that gets on these steel bridges leads to decay, to rust. And this rusted connector is 27 years old, made with rust-resistant steel, as this one is 28 years old. And this one, you have to use structural paint to keep this guy going. And this one. So, just because it's steel and concrete doesn't mean it lasts. So what are the conditions for decay with timber? This is kind of a rain exposure zone in North America. And any place where we see lots of precipitation, we see opportunity for decay. And therefore, in the prairies, our timber bridges tend to last longer. They don't get as much decay unless you vertically spike them from the top and let moisture into the middle. So these are the ingredients for decay: 5 to 35 C, moisture over 22, oxygen 21, and a food source. Now I'm going to make a comment. We finished an exhaustive study with over 1,600 core samples from many bridges around the world and wrote a report that was going to be presented in Australia if it hadn't been for COVID in February. And it's now going into the commentary of S6, part 9. And we found that the average moisture content in a closed deck bridge was 14%, and the average moisture content in an open deck bridge was 16%. Both of those percentages are less than 22. If decay needs 22 or better to decay, why is decay 82% of all timber bridge degradation? It's because of our fastening details, our connection details. So fungal growth is fastest in these ranges, as you can see here. And, we have to have moisture. So if we can eliminate moisture, or we can change our fastener system so that it reduces moisture, we're going to get longevity in our timber bridges. Oxygen has to be over 21. And if I permanently submerge timber in water, then it won't decay because there's no oxygen unless marine borers get it in coastal environments. So I often see engineers will come up to an old timber bridges where they've got piles in the abutments, and they'll say, let's pull all those timber piles out because they've got to be decayed underground. They must be terrible. And I say, well, that's the worst thing you could do. Leave them in the ground and use them for mud sill piles, because the wood down under the ground will be as good as the day you buried it because there's no oxygen. The food source, of course, is wood. So just a few pictures. Look at this one. That's kauri, dug out in Western Australia. They found it when they were digging it. They figured it was in the ground 10,000 to 50,000 years. Look at the guy standing on it. Look at this guy. He's in the bayou in the southern part of the United States. It's a southern yellow pine log. He's in the water with the alligators, not because he thinks it's a good time, but because this log is worth a lot of money. It's been submerged in fresh water and it's not decayed. They're harvesting it to make flooring out of. Well, look at this. I took my daughter one time to a King Tut exhibit in Perth, Australia, and they had all these exhibit items that were in the Pharaoh's tomb, and they're all made from wood, and they're 3,000 years old, and they're not decayed. Why? Because there was no moisture. Look at them all, still intact. You know, a guy skidooing across northern Manitoba, and he sees a stick coming up through the snow, and he stops. He looks at the sticks. He digs around the stick with a spade because he's interested in it. Well, he marks the GPS location because there's no other wood around. Marks the GPS location. Goes back later, and they dig down and find what? The HMS Investigator that got locked in the ice hundreds of years earlier and was still intact, with the bedclothes and the skeletons and everything else. The people had all died on it. And the wood was still intact. What was missing? Temperature. The bridge was literally put in the fridge and didn't decay. So we can remove any one of moisture, oxygen, and temperature, and decay does not occur. So how do we prevent decay in our timber bridges? What are the top 10 things we can do to prevent decay? Well, the first is we can stop putting vertical fasteners through from the top, connecting our decks to the girders underneath. It's the single biggest thing we do wrong today with timber bridges. I tell my students, look, stop using vertical fasteners from the top, and you'll extend the life of your timber superstructure threefold. Stop the use of meltoid barrier. That's putting pieces of metal and bent metal around wood that will sweat and keep holding moisture in and around the wood. Make sure there's drainage. People often say, well, it's a loose deck. No sense of having a drain, Dan. Well, that's untrue. You need drains in timber bridges. Provide for moisture content induced change. When you buy a big dimension timber, 8x12 or 8x14 or 8x16, it's not dry. And so when you put it in place, it will dry because remember the average moisture content was 14 to 16. It will dry out. And when it does, it shrinks. And that creates looseness in the bridge. Stop the use of banding. You'll see it on piles, timber piles all over the place. The minute the timber pile starts braiding at the top because they vertically spiked the cap into it and it let decay in the middle, it starts to split and braid open. Well, what do? Band it. But nothing stops the tree annulus or the log annulus from buckling inward when it's banded. Stop near-end drift bending. Provide proper clearance for breathing. Heavy percent solids, I talked about it earlier. Stop notching and use the proper size timbers. Let's look at a few of these now in detail. Look at this. This is in outside of Port Hope in Ontario. Look at this, a vertical drift pin into the top of a pile. It completely decayed it out because it let moisture into the bright wood, untreated wood. Look here again, untreated wood. Look here in these girders where the deck was spiked. They had to all be taken out. Look what happens. The spike lets water into the bright wood, untreated wood, and they decay. Look at it here. This is so typical in timber bridges. It's why timber bridges get a bad name, because the maintenance cost goes up for them to keep them going. And they'll go out and replace and do the same design detail in the replaced item that they built it with. And why? Because everybody knows timber is out of vogue. And who wants timber anymore? We're going to steel and concrete, and we'll just keep this bridge going long enough to replace it with steel and concrete. And that's what's changing today as we see new timber bridges get designed and built and better techniques for maintenance being used. Stop verticals. Stop verticals. Switch out the verticals for horizontal. You see in this whole bridge system, they're switched to horizontal. Switch to horizontal. Horizontal here, horizontal here. Stop meltoid barrier. And then, they put meltoid barrier and then put a vertical bolt through it and the water sticks underneath it and it leads to decay. Here's another one here, meltoid barrier. Meltoid barrier, look, took all of the girders out. They put a new precast concrete top on it. They put lag screws down through meltoid barrier from the top, put wells in them so that the water would hold. And within 6 years, the bridge was gone. Better drainage. Don't let drainage come on the wood. If you care about drainage on a galvanized pipe, care about it on the wood. Don't let the water come out of drain and get right onto the wood. Now look at this here. This drain was installed on a bridge. They went out and put them at 20 foot on center, and 20 foot on center landed it on every cross bearer. They didn't bother to put a $2.49 extension that would have taken the water off this cross barrier. After they put the drains in place, 3 years later, they started having potholes above. This guy got decayed, he lost capacity, started to lead to a pothole. They sent a guy out with hot mix to fill the pothole. He looked around, saw this guy was compression failing, perp to grain. So he suggested they have to have a sisters. So they come out and put 2 sisters in. The sisters can't get in at the same size, so they have to put them in at a shallower depth. So they put in 1 packer. Well, soon enough, the sisters dry out, shrink up, and they get loose again. Another pothole develops. They send them out again. They have to put in another packer. And the whole time, this decay is spreading into this piece and decay in this piece. And each time they've been out there 3 times in the total, they went to the job site. Never a time did they install a $2.49 drain. A lot of times, nothing fixes stupid. And so if you see timber as false work, temporary work that will not go the distance in your bridge, you're going to do stuff like this. I see timber as a long-lasting material, not as a short-term material, but as a long-lasting material. We allow for shrinkage. Look at these lift buckets. They're cylinder on cylinder. They'll turn 360 for adjusting skew. They have nuts for lifting up and down. They got neoprene pad underneath them here. And this whole thing lets the bridge move up and down and change for skew. Here, the same. Allow for moisture change with these slots right here that lets the deck shrink this way when this guy isn't shrinking this way longitudinally. And dome compression band, you see them here, 2 of them. What happened? Well, he put the first one on and it fell down here because the wood shrunk and it buckled in. He had to put a new one up top. Here, it started here, here it ends up here. You got to know compression bands aren't working when you have to hold them up with a finish nail. Why? Because the wood shrinks, it buckles in, and the compression band slips down the taper of a pile, like here. Near end drift pinning, don't do it. Leave some space for the wood to breathe. Always be thinking about wood breathing. Don't fill up concrete around your wood piece and not let it breathe and dry out and then wonder why it decays, like here. Building up riprap all the way around these whales and basically leading to a bunch of air, a bunch of moisture, and subsequent decay. Bent metal tops on your post, they don't work. If you're going to use them, you have to have space to let the wood breathe. Best thing here is really a slope cut. Copper naphthenate heavily and anchor seal a paraffin wax and water. The same goes here. Stay away from the solids paint. You put the solid paint on a curb, the first thing you know, the curb's decaying because it can't breathe. And don't notch. Look at these notch. What does notching do? It creates abrupt stiffness and causes peeling or tension perp. And you see this reentrant corner crack continues. This is a terrible place to notch a girder in the middle just to put a diaphragm beam in to cause them all to be an equal yoke. It doesn't work. As you can see here, this bridge then ended up having to be replaced. You can see the reentrant corner cracking. This is called sniping or notching and is ineffective. You need at least a 6-to-1 slope off a notch. See it here again. And you don't use the proper size caps. Typically, piles and girders were matched so that the girder would drop loads right into the piles. Well, with the advent of heavier loads at the turn of the century, we started putting more girders in place to increase our superstructure, not thinking about the fact that we were dropping loads further away from the pile. We could neglect the load, the distance D away from the support, but when we started putting them in the middle, all of a sudden horizontal shear cracks started to show up in our caps because we had not properly sized the cap. Secondly, you look here, 2 horizontal bolts joining the cap and the pile. Never enough. We have to calculate the capacity because the wood shrinks away from this notch, ends up carrying the load on its own, and 2 will never work under conventional loads. And why would they go back and put a new one in with 2? Well, no brainer. That's what it used to be for 100 years. And everybody knows we're going to replace this bridge in 5 years. So don't spend a lot of money on it. So the advantages of timber bridges are important. It's low self-weight, 1/8 the dead weight of an equivalent concrete bridge. I just designed a timber bridge called Glulam Bridge outside of Halifax. It's 35-meter clear span. They didn't even put concrete in the tender, Nova Scotia DTI. Why? Because the dead weight of concrete would have made it too expensive at 35 meters. When the tenders start opening up to timber all across this country, concrete girders that are used in spans longer than 20 meters will be definitely uneconomical. Concrete sweet spot is 15 to 20. The minute you put a 35-meter concrete span in place, timber at 1/8 the dead weight will be so much more savings. It's not practical to use concrete anymore. How did concrete get in and how did timber leave? When I started designing in the 70s, timber was still in vogue. By the time I get to my point, I'm 66 now, or I'm at the end of my career, timber's out of vogue. Why? Because concrete won in the 15 to 20 meter slot and then won everywhere else under the auspices of it lasts longer, which is simply not true. So wood allows smaller substructures, longer spans, self-weight. People say, well, you can't design long spans, Dan, with timber. Well, that's just simply not correct. My longest clear span building is 535-foot clear span, 12 stories high. My tallest design building is 20 stories high. My longest timber bridge is 179-meter clear span. Think about it. Ask around and ask some engineer to tell you where there's a concrete, precast concrete girder under bridge that's 80 meters long. You need to send me an email. I want to know where the precast concrete girder under bridge that's 80-meter clear span is. You won't find one. The reality of it is timber spans further than concrete because of its dead weight. The reduced transportation cost, reduced heavy equipment on site, rapid installation because components can be prefabbed, large assemblies, and sometimes allow the entire bridge to be placed. It's lightweight. It allows this to be achieved with smaller equipment, minimizes interruptions to traffic, and reduce labor costs. Look at this one. It's a 10-meter center span in a 2-lane with the sidewalk bridge. The whole span, deck and girders and connectors, all dropped into place with one crane that the previous week could only lift one precast concrete girder of the same span. The whole pre-assembled span laid less than one precast concrete girder. So initial savings and initial construction costs compared to steel and concrete are big. They're significant. The superstructure material costs are competitive with concrete and steel, and low self-weight and rapid installation really make a difference for our timber bridges. Of course, reduced carbon emissions are big these days. When we think about this carbon, it's important. Our federal government just made an announcement saying they want zero carbon issue in all of their structures that they support. They said buildings, but we expect to see it come to bridges, and they haven't quite got there yet with bridges. The minute they say they want them carbon neutral for all our bridges, timber will be hands down, far and away, the best option. Look at this bridge in Quebec. Look at these numbers. The total carbon emissions savings, 1,466 for this bridge in timber. That's a huge amount of savings. This Nepan arch that I showed you earlier, look at this, minus 350 tons versus 3,200 total tons in carbon for the steel alternative. Minus 350 plus 3,200. Why? Because wood uses photosynthesis to convert carbon into oxygen. It's great for us. Growing trees is great for our planet. It converts carbon to oxygen. Our wood sequesters carbon, holds it in place, and the greatest block of sequestered carbon in the world today is in the building, the stick-built timber buildings built in North America. It sequesters carbon. Wood is naturally resistant to chemicals. When you spread salt on the road, it takes out your concrete decks. When you spread salt on the road with wood, it preserves the deck. And so wood has this natural environmental resistance to different types of chemicals, which makes it great for various climates and various exposure conditions. Its resistance to freeze damage. Its repetitive freeze-thaw cycles can be accelerated, and cracking in concrete will take it out when it doesn't in wood. And cold temperature, of course, do not affect the structural performance of wood. You can use high strength fiber, which is an area that I've put a lot of time into over my career, having first developed it back at UNB many years ago. And we use high strength fiber to get where we're going. In this Milky Bridge, which I'm going to show you here in a minute, in this Milky Bridge, or I showed you earlier, I guess, you'll see the high strength fiber goes full length. We have it on a roll. You unroll it. You take it out full length and adhere it to the bottom of the wood, and it's 5 times the strength of steel in tension. And it joins to the wood, and it doesn't have a coefficient of thermal expansion like steel, because you couldn't bond steel to wood, because thermal coefficient of expansion is so different that the steel would spald off from the wood. So we use this fiber reinforcement to do funky things. Here it is on a long roll. We unroll it, prepare the surface, and bond it to the bottom of a big beam. And we can increase the beam's capacity 2.5 times. That means that the same depth goes a lot longer. Half the width goes a lot longer. And this allows us to be able to reinforce the bottoms of our girders and get where we're going. Or we can use shear plywood here that has off-axis fiber that enhances shear capacity and increases the beam shear capacity, so you don't have to have another size up. Or wrap a pile with high-strength fiber in various orientations so that we don't have to take the piles out and frame bed them. We can fix them in situ while the trains and equipment are on the bridge. We can use high-strength retrotens to increase the strength of a girder in situ and wrap and do all of this work to improve performance of existing structures. And that's going to be in our maintenance webinar coming up. As you can see here more, this is in Richmond, BC. So in the last 20th century, we've had a resurgence in timber just in this last decade or two. As you can see with these beautiful bridges that we've talked about in terms of timber. This is the longest 3-lane clear span bridge in Canada, 39.5, roughly 40 meters, 3 design lanes, clear span. And it's the longest timber clear span 3-lane design bridge in Canada, right in Amherst, right in Atlantic Canada. You can see here's a beautiful bridge, kind of mimicking the rainbow arch that was there before in the steel one. And it's fitting. It's fitting for me. You know, it's nice to be back home here. I live in Jacksonville, Florida now, and look after the engineering for all our different offices around the world. And it's nice to be home, and better even yet, to be close to where I grew up in Albert County, New Brunswick, and see a steel bridge be replaced by timber that lasts a longer time, is lighter weight, is spanning the distance, and doing it with 3 lanes. That's a great story for me to tell in terms of my career. As you can see here, looking down the line, these big finder plates, and you see the shear panel here doing the job. A transverse triple T bridge. That's the Glulam deck, longitudinal. It goes transverse with a Glulam girder system and hanger rods. And this is we built a tray at the full length to go along underneath and inspect it when we need to, because I strain gauge the whole bridge so that I can count the number of garbage trucks going across every week and understand what it's doing to the bridge, as you can see here. This is shots of it being assembled. It was totally assembled in one of our plants out in Oregon. And you can see here the whole arch being assembled. It took 60,000 pounds to squeeze these pins through the finders. And then they were all taken apart, sent out for galvanizing. You can see the height of this man in terms of give you a scope of the truss. We put this 500-ton crane on the jump span, which is timber, that was supported by piles that were 80 years old with new timber piles. And the engineer of record for the province said, "Where are you going to position the crane?" And I said, "I think the best place to put it's on the jump span." And he said, "A jump span? You'd never put the crane on the jump span, would you?" And I said, "Why wouldn't you?" "Well, you couldn't do it because you just finished the bridge." I said, "It isn't concrete. I don't need 30 days to cure it. I just got it done. I'm going to build this arch right beside it, and I'll lift it up with a 500-ton crane and drop that arch into place in the gap." As you can see them here, placing it over the triple cap. It shows you putting it together, the pre-assembly of the T's in Amherst, and then working through the night to get everything done on time and put into place. So quickly, the whole deck went into place in a day. And the day we were done the deck, I was the first one to drive across the bridge. Could have I finished a cast in place concrete deck and drove across it 8 hours later or 6 hours later? No. These are tremendous advantages for us with timber. See this one out in BC at Sun Peaks, K162 bridge. It's got a timber abutment, a bearing abutment, and a timber, you can see it here, a TL4 truck crash-proof rail system. And the abutment is buried in the ground on bearing pads. There's no driven piles. And the girders were high-strength fiber reinforced. You can see it here. And the whole bridge was built inside the plant with a truck crash-proof rail system, a 2-ply deck system that could lead for changes if there was a deck damage. And you can see here the attachments that were necessary for the TL4 guards rail system. This is Meadow Lake, where you had a 52-year-old railway bridge that had been decommissioned for 10 years with a line pulled up. And the forestry company that owned it wanted to restore the line and start hauling one way to stop the problems they had during spring breakup. So they had a good heavy haul road bed here. And basically we restored this old bridge that had been decommissioned for 10 years, put a new deck on it, and opened it up to L110 loads. That's heavy duty truckloads on an old bridge. So there's an old bridge out of service, being inspected, finding the bad actors, fixing the bad actors where they needed to be fixed, a new transverse deck put on it, and put back into service. That's the way we like to see wood go and be continued in its use. This is in Providence Road in Ontario. As you can see here, old and new. Fix the old, put the new. Restore and extend life. Old and new. Snake Road in Hamilton, Ontario. Beautiful bridge. Use the old, put the new on it, and put a 2-laner back in play with good service for the community, because they didn't want to have the bridge tore up and the intersection on the other end all raised up. They want to be able to keep this old bridge in service, as you can see here. Dickinson Road up in Ontario as well, a pretty bridge. The old and the new, using the old and the new to go up over a railway line. Old, new, new, old. This one here in Glulam Bay, Washington, back it's at least 25 or 30 years ago when I just started with high strength fiber. We put these girders into place, and they were totally treated after machining, and we installed gauges in the high strength fiber area to be able to tell when the tides come in and so on, and what effect that had on the bridge. This is one I have designed in Austria. As you can see here, transverse shear girts. It was a beautiful bridge made out of reinforced glulam. They couldn't get the arches in the retort, so we put a roof on them. Over in Scandinavia, they've been leading the way with this new timber bridge move. You can see here 47-meter single spans coming on. They're really moving ahead. And in Scandinavia, most of their bridges are not treated. They have to find ways to put roofs and covers over them to extend life. As you can see here, 47.7 meters. That's the total length of the bridge. Interesting designs, all coming in timber. It's post-tension transverse, vertically laminated transverse post-tension. Starburst kerf plates, louvers on the side to keep the water from getting at the side of the piece, with a popped up bent metal top system to create roofs, as you can see here. Let the wood continue on underneath with no treatment, and kerf plates here on their pins and the finders. It's another one here, total length of 147. The main span in the middle is 70 meters. A pony truss, you can see the arch going here with the web elements in the bank piers. You see this multi-span, 36 meter each span timber bridge, 5 spans. These bridges are coming back. Timber is coming back, and in a big way, as you can see all over the world today. And this means that there's this change. The pendulum swung too far over to the concrete steel option. And concrete was not the panacea we thought it was. Concrete bridges are blowing up on them at 40 years. Spalling, reactive aggregate issues, and so on, are meaning that concrete just doesn't go the distance the way they said it would. It isn't going 100 years. And we have evidence that timber bridges do because there's plenty of them around, like 54 covered bridges in New Brunswick that are 100 years old, as you can see here with starburst kerf plates and dowels. Beautiful bridges and timber, resurrecting the opportunity to see timber go the distance and be in popular use scenarios again all over the world. And it's happening here in Canada. And we're designing lots right now just for this reason, because governments are beginning to realize that it's not just about carbon, it's about benefits, the savings, so on. That Roger Bacon Bridge, the Rainbow Bridge in Amherst, was $6.5 million in concrete, 3.7 in steel, and 2.9 in timber. The Dillman's Bridge, the same types of responses. Concrete was double. Now they're opening up all their tenders to timber because it's driving down the cost of concrete and steel. At the same time, timber is coming in and showing that it's a good use opportunity for various functions. Any time you take and you have three materials that are there to compete and you take one out and only allow the other two, it drives price up. And so governments are realizing that they want to keep their prices down. You see this Cowley Creek Bridge, 16.5 meter, 2-lane bridge. They assembled the whole thing and lifted the whole bridge at one time onto the finished piers. You can see here, one crane lifts the whole bridge and away it goes into service. Alderley Avenue, the same thing, pre-assembled in a weekend at 8 o'clock on Friday night. They gave us the permit. They de-electrified the lines because the electric trains. And by Sunday night at 8, we had built a bridge across this gap for 2 railway lines, 3 spans, heavy skew. And this is the same here. 7 o'clock on a Friday night. On Sunday night at 8, we had the bridge finished, put into place, and traffic was on the bridge, and trains were going underneath it. And not often could you do anything like that with concrete and steel. And if you did, the cost would be significantly higher. Newry Island, the same thing. In 11 days, we had to take and use a ferry to get old folks off the island. And we restored this 62-meter bridge, working around the clock to put a single lane across. The temporary sidetrack bridge that would have needed to be built cost more than restoring the timber bridge, putting water lines back in and so on. So this shows you just how timber has come back now in vogue around the world because of the way it's at. I think the summary and conclusion for us today, I've ran over a little, is that timber is coming back. It was here for a long time because it served a purpose. People forgot about what that purpose was in the light of what seemed a better solution, steel and concrete. It hasn't lasted the way they wanted, and we're now looking again to timber. With the proper construction details and methods for design, timber bridges go the distance and can properly be designed for a 100-year lifetime and last many, many years longer. Maintenance and design are 2 key aspects of that, and the next 2 webinars will talk about design, proper design strategies, and then proper maintenance strategies for timber bridges to extend life. Thank you for putting up with me for this time. I look forward to having you in the next 2 webinars, and if there are questions, I'll take those now.
Awesome, Dan. Thanks for that that great webinar. We do have one question so far. The malthoid barriers, the peel and stick flashing, are common for residential wood decks, top of joists below the decking. Does the problem occur when larger timbers cannot dry out versus a light 2x member?
I understand you. The only place that maltoid barriers should be used is between concrete and a piece of wood that's resting on concrete. That prevents the moisture from licking up into the wood. It's there as a impermeability layer to keep water from transferring to the timber. Where maltoid has the problems is when it goes between wood layers. Oftentimes you'll see maltoid used between a deck plank and a timber girder, and then they drive a vertical spike through it, and the vertical spike lets water follow the spike trace down. The maltoid barrier harbors the water and allows for more decay in the superstructure. Just let it breathe. When you use maltoid on top of things like shed roofs and bent metal on the tops of things, make sure it's always got lots of air to breathe, because every day the bent metal will sweat and bring moisture to the wood, and that accelerates decay. So much of what we see today with our detailing are wives' tales and pass-me-downs. Look, at the turn of the century, wood was cheap and men were cheap. And so we could fix bridges and build them cheaply. Today, the cost of labor and mobilization and dealing with these hassles is so much higher. People want maintenance free, and they think that concrete gives it to them. It doesn't. The Swiss Institute has come out with a publication, which we'll be glad to share with you, that shows that a properly designed and detailed timber bridge has a lower annual maintenance cost than a concrete or steel bridge. It's all in the maintenance detailing that drives up the maintenance cost. What's next?
That's great. No more questions thus far, but we'll give it a couple more minutes. If you have any questions, be sure to type it in the Q&A section down below. I did add in the chat box there, the completed research that was recently done by Wood Research and Development, Dan Tingley's group there. I add the link in the chat there that will take you directly to that research document. So be sure to click that and save it somewhere.
Any other questions people have? It's a little bit difficult in a webinar. I know you have to type them in versus standing, sitting in a chair and I'm up front. You can ask me and I can point to a slide. But if you have questions that come to you, just send them to us in an email and we'll handle them that way.
Yeah. Okay, it looks like it's good there. So yeah, the next webinar will be on, or next Tuesday, I guess, at 2 o'clock, same time. And it'll be on design of timber bridges. So be sure to register for that. We just did get another question come through there, Dan. So what are good replacements for drift pins at the end of logs or timber girders?
I understand you. That's a good question because we often see drift pins used. And the term I use is near end drift pinning. What happens is they'll use them when you're building a cribbing, for example. They're very common in Nova Scotia to have cribbing piers and cribbing at abutments. And they'll either be an open or closed cribbing. That means there's an infill to make them closed to hold fines and smaller aggregate, or they're open faced cribbing where they're intended just to hold large aggregate. Well, when you take the corners, they drift pin them, and drift pin standard hole-to-hole ratio, that's the diameter of the drift pin versus the diameter of the hole. The hole was smaller at 0.9 for softwoods. And so the idea was we would join them with this vertical drift pin all the way from the top. Well, we would buy CCA treated wood or, other creosote treated wood. Then we turn around and drill a hole in them into the bright and drift pin into that bright. And the water would follow the drift pins in, get into the bright core, which is untreated. And it wouldn't matter if you had 1,000-year lifetime in your treatment annulus. If the bright got exposed to water, it's going to decay. And so as a result of that, the drift pinning has often been an Achilles heel for timber. And so when we talk about the ends, what we talk about is typically with fasteners, we like 7D, that's 7 times the diameter of a drift pin to the pilot hole. With 0.9 used for a drift pin, a typical pilot hole for a leg screw would be 0.7 of the root diameter of the thread. A typical pilot hole for a bolt is no more than a 1/16 of an inch larger than the bolt diameter for bolts up to 1 inch. And there's a reason for that, in that our bolt design values are based on pilot holes being close to the shank of the bolt. When they get to be big and sloppy, the design values drops tremendously. So we typically like 0.9 of the pin as a pilot hole in softwood, and we like to be 7D away from the end to where we put it in place. And as you know, I don't recommend drift pinning the corners of cribbing. I recommend saddle systems with all horizontal, as I showed in that picture. So your saddle system is what I recommend, and the pieces of wood that are coming up to the corner in a cross-hatched fashion would rest in saddles, successive saddles, cheek plates, and then you do a horizontal bolt through it, and horizontal is going to outlast a vertical by a factor of 3. So just saddle them in, and if you'd like to ask me, put an email to give me, and I'll send you a little sketch, show you what they look like. There is a limit for arch radius. Another one of the question from Edson is, what's the limit for a radius? Well, what happens with timbers when we make the radius is that the tighter the radius, the more radial tension in the element. And when we get smaller and smaller radiuses, we have to go to 1-inch thick laminations nominal from 2-inch thick laminations. So the tighter the radius, then the thinner the lamination so that it bends. Now, there is a limit. As you get into these limits in terms of radius and inches, you get down to 900 and 800. These are become too tight a radius, and they'll put too much what we call radial tension on the joint, and it'll want to pop the laminations apart down road. They get into tension perp. And tension perp is wood's weakest direction of strength. Wood is an anisotropic material. It has different properties in different directions, and its weakest strength direction is tension perpendicular to grain, where it's like 15 psi or 0.1 MPa versus, let's say, 2400 psi in bending or 16 or 18 MPa. So as you can imagine, it's huge difference. So we don't like wood to get into tension perp. That's how we split it. When we split a wood with an axe, we take the kinetic energy of the axe head going over our shoulders, and we got an inclined plane to them with the wedge of an axe, and that kinetic energy transfers to tension perp energy, and you split your firewood for burning every year. That's how we split firewood. So wood is not really good in tension perp, and so you got to watch the radius of your arch in terms of not creating too much tension perpendicular to grain. Thanks, Edson. Who else has questions?
Hey, that looks like all the questions,
Okay,
Dan. If anyone does have any questions, feel free to reach out, and we'll get those answered for you. Besides that, thanks for joining, and we'll see you next week.
Thanks, everyone, for putting up with me for an hour, and we'll look forward to seeing you next week.